Welcome to the celestial sphere. Have you ever looked up at the night sky and wondered how astronomers know exactly where to point their telescopes? It seems like a giant, dark blanket with millions of sparkly dots. How do they find one tiny star among so many? The secret isn't a magic trick, it's math. But it's not the kind of math you might be used to from school. We're talking about a special kind of geometry that happens on a sphere. Imagine drawing a triangle on a flat piece of paper. Now, what if you tried to draw that same triangle on a basketball? It would look different, right? The lines would curve. This is the amazing world of spherical geometry, and it's the key to mapping our universe. Astronomers use a cool concept called the celestial sphere. It's an imaginary giant ball that surrounds the Earth. All the stars, all the planets, all the galaxies are thought of as being on the inside surface of this ball. Of course, we know they are all at different distances, but this idea makes it much easier to map them out. It's like having a giant globe for the cosmos. When we want to connect three objects on this celestial sphere, say 3 bright stars, we don't use straight lines. We use curved lines called great circles. A great circle is the biggest circle you can draw on a sphere, like the Earth's equator. When 3 of these great circle arcs connect, they form a spherical triangle. These special triangles are the backbone of observational astronomy. So, what makes a spherical triangle so different from the flat ones we draw on paper? It's all about the curves. Let's start with the angles. In a flat triangle, the 3 angles add to exactly 180 degrees. It's a rule that never, ever changes. But on a sphere, things get wild. A spherical triangle's angles always sum to more than 180 degrees. The bigger the triangle, the larger the sum. Small triangle example, about 180.1 degrees. Huge triangle example. The angles can get much larger. Imagine you're at the North Pole. You walk straight down to the equator, turn 90 degrees and walk a quarter around the world along the equator. Turn 90 degrees again and walk straight back up to the North Pole. You just walked a giant spherical triangle. You made 2 90-degree turns and the angle back at the pole is also 90 degrees. So, what's 90 plus 90 plus 90? That's 270 degrees. Perfect example of angles way greater than 180 degrees. It's a mind-bending idea, but it's how geometry works on a curved surface. The sides of a spherical triangle are different too. In a flat triangle, the sides are straight lines measured in inches or centimeters. How do you tell a friend where to look for a specific star? You can't just say, "It's up there," to the left of that bright one. That's not very precise. Astronomers needed a system just like the latitude and longitude we use to find places on Earth. And that's exactly what they created for the celestial sphere. This system uses 2 special coordinates, declination, right ascension. Think of them as the celestial version of latitude and longitude. They allow us to give every single object in the sky a unique address. This cosmic GPS is built entirely on the principles of spherical geometry. Declination is the celestial equivalent of latitude. On Earth, latitude measures how far north or south you are from the equator. In the sky, declination measures how far north or south a star is from the celestial equator. The celestial equator is just Earth's equator projected out into space. Stars directly above the equator have a declination of 0 degrees. The North Star, Polaris, is very close to the North Celestial Pole, so its declination is almost plus 90 degrees. The other coordinate is right ascension, which is like longitude. On Earth, longitude measures how far east or west you are from a special line in Greenwich, England. In the sky, right ascension measures the east-west position of a star. Now that we have our celestial coordinate system, let's put these spherical triangles to work. One of the most common things an astronomer wants to know is the distance between 2 objects in the sky. I don't mean their actual distance in light years, but their angular separation, how many degrees apart they appear from our perspective on Earth. For example, angular size of a constellation, how far apart the 2 pointer stars in the Big Dipper are. This is a perfect job for a spherical triangle. It's like using a cosmic ruler to measure the heavens. Here's how it works. Let's say we want to find the angular distance between 2 bright stars, Vega Altair. First, we look up their celestial addresses, right ascension, declination. Now we have 2 points on the celestial sphere. What's our third point? The North Celestial Pole. Using the spherical law of coziness, we calculate the length of the third side. That third side is our prize, the angular separation in degrees between Vega and Altair. The use of spherical triangles in astronomy is not a new invention. In fact, it's an ancient science that has been essential for centuries. Ancient astronomers, the Greeks, Persian scholars, Arab scholars were masters of spherical trigonometry. They didn't have powerful computers or digital cameras. They had their eyes, astrolabes, and a deep understanding of geometry. They used these cosmic triangles to create the very first star charts and catalogs. By measuring the angles between stars, they could meticulously map the heavens and predict the movements of the sun, moon, and planets with incredible accuracy for their time. These ancient skills were also crucial for navigation right here on Earth. Before GPS, sailors navigated the open ocean by the stars. They would measure the altitude of the sun, or the North Star, above the horizon using a sextant. Today, we use the same fundamental principles for something even more exciting: space travel. When we send a probe to Mars or a satellite into orbit around Earth, we have to navigate through three-dimensional space. Mission planners at NASA and other space agencies use sophisticated versions of spherical trigonometry to calculate these trajectories. It's amazing to think that the same math that helped people draw constellations now helps us fly among them. The power of spherical triangles goes far beyond just finding the distance between two stars. This amazing tool helps astronomers solve a huge variety of problems and understand the sky in a dynamic way. One key application is converting between different celestial coordinate systems. We talked about the right ascension-declination system, which is fixed to the stars, but an observer on Earth often uses a different system based on their local horizon, called the altitude-azimuth system. Altitude is how high an object is above the horizon. Azimuth is its compass direction: north, east, south, west. To point a telescope, you need to know the star's current altitude and azimuth. But a star's altitude and azimuth are constantly changing as the Earth rotates. Its right ascension and declination, however, stay the same. So how do you convert from one system to the other? You guessed it, with a spherical triangle. This is what the software in modern computerized telescopes does automatically. This same triangle can also tell us the best time to view a celestial object. For example, it can calculate the exact time of sunrise and sunset. Every aspect of the apparent motion of the celestial sphere is described by the rules of this unique geometry. It is the language that translates the static map of the stars into the moving, living sky we experience every day and night. From the very beginning of human curiosity, we have looked to the stars and sought to understand our place among them. The journey from simply gazing at constellations to precisely mapping the universe has been a long one. The humble spherical triangle has been our guide at every step. It may seem like an abstract mathematical concept, but it is one of the most practical and powerful tools for exploring the cosmos. It bridges the gap between the flat world of our everyday experience and the grand, curved reality of the heavens. It gives us a language to describe the sky, predict the sky, navigate the sky. Learning about spherical triangles does more than just help with astronomy. It encourages us to think differently about space and shapes. Angles adding up to more than 180 degrees introduces non-Euclidean geometry, which Albert Einstein used in his theory of general relativity. So, the next time you look up at the night sky, I hope you see more than just a random scattering of lights. I hope you can imagine the invisible lines connecting them, forming giant triangles that span across constellations. Now go out and discover some triangles for yourself.